All right. Welcome, everybody. So now that we are in the very deep in the semester, so we have we went over like a lot of content in the class, including CNNs, and I mean from like multilayer perceptron CNNs and other content from until last week when we saw the last 2 weeks we saw GANs and a little bit of transformers. We are going to continue with now this tutorial about how to implement a three-dimensional generative adversarial network. So we will go over some code. I will start by sharing my screen. So let me adjust the size. We are going to do not what I have on screen. So actually, just let me just do a new notebook. Let me move this a little bit. What we will do, and I think I told you once, one of the main problems about 3D GANs is that in the end, I mean, it's interesting. It's an interesting technique, could be useful. A lot of things are obviously deprecated and so on and so forth. I mentioned this like many times in the past 2 videos, but it's one repository that actually implements a couple of things that we want to do. If you want to do this locally, it's fine. You don't need like super crazy hardware with a 1070 or like a good mobile GPU like 20 series or 30 series. You're good. So you can get results like this. And we have a code. We will go like very easy through this. So this repository, for example, uses again the MAT file format. So I made some modifications that I will show you for this. So I will start just with a Colab, notebook settings, GPU. I'm going to use high RAM in case I want to train with better resolution. We're not going to focus on importing the data that we produce yet, although we could, but I want to focus on setting things up. So just let me, I have too many windows open. Okay, so I will go like step by step. Step 1. So this will be the 3rd video in the series. There will be a 4th video when we actually like implement everything, basically like all the steps, and maybe a 5th video on how to use this outside Colab. Probably, yeah, to actually do the project that I showed you in the first video, the sketch to shape. Anyway, so we will start installing TensorBoard X. TensorBoard X, we will import torch. Oh, I'm writing this on the here, and first like import. Remember that when we have the exclamation sign, it's because we're using terminal commands. As we saw in the class, you know, like 3D GANs are basically the interplay, right, between a generator and a discriminator. Being a generator, at the beginning, a very like dumb model that only knows how to produce noise, right, or is giving noise as an input, or starts from noise. And you have a generator that basically it judges or basically discriminates what the generator is doing, right? So based on that, and basically like through optimization and backpropagation, and all of the things that we have seen in class, it tries to get better at coming up with a let's say like the structure of the image and making better and better images. And we saw in the class that this was like amazing, one of the major breakthroughs. Ian Goodfellow, I don't know, like skyrocketed in the world of computer science with a lot of citations, and it's crazy because they are super useful for many things. But this idea, although very simple, it's actually quite interesting, right? You have a network that basically learns how to improve over time based on a judgment from another network that is saying that this image is false and or true. So the generator improves, but also again the discriminator also gets better at basically like at judging if something is fake or not. So imagine that at the level of a in 3D, right? And this is using deep convolutional neural networks. And in this case, this implementation here basically is a DC GAN that tries to replicate the original paper, and we're going to use this as a foundation for our code. So basically, in this case, it's like not judging like the information from a grid of 2D pixels, basically like a 2D image, but basically now we're adding a third dimension, which makes this like harder as a problem. But it's not that different to like a simple implementation of just a, for example, a DC GAN. Let me see if I can show you an example. I might have something. Actually, yeah, I have pix2pix here. Let me just close this. Pix2pix is not what I want. Yeah, so for example, this is a Colab that I can also like show. It explains the nature of DC GANs, but the idea is that you will have a this is data, but I want to show you the implementation. Basically, you always in a 2D or in a DC GAN, a normal DC GAN, you have a generator, right? That basically is doing like a lot of like upscaling operations, because this is a deep convolutional GAN. And you have, in this case, you create the generator, and you have a discriminator that will take that information, it will analyze it, and it will say like, no, true or false. So this is interesting because then you can create your network. You define like a several like loss functions and optimizations to improve, and it just goes and trains what is based on images. The only difference, or basically like one of the, not the only difference, but one of the things that we're going to do here is that we will add one more dimension to this. So that is actually quite interesting. So let's just start defining the generator. Actually, let me make this a little bit bigger. Our GAN. First, the generator. So let's see how can we do this. So we're going to create here first a class that will be like the net G, our generator. It will take torch.nn that module as an argument, as a parameter. We'll create a constructor. And here we can start writing our net. So we're gonna say like net G self And we will say that self.args equal args self. We can give, for example, a cube length. So that means like the dimension of the voxel space that we're going to use. So for example, if you don't have Google Colab Pro, you might want to keep this as a 32 by 32, which is going to give you like very basic models. But if you try to deploy this, for example, using a IPython notebook, if you have like a decent GPU, you can get actually like pretty good results in reasonable time with 64 by 64. 128 by 128, probably it will use all the RAM that you have available in your Colab, so you won't be able to use it. So I explained a little bit about that in the past video, so I'm not gonna stop with that. So we're gonna say like params that ulan self. We need to specify a self that bias self that C dimension, basically to then to do like an also like the dimension of the latent vector that we input to our network, and self that f dimension equals 32. Here we have all of our parameters, I think. We need to specify also, we have a, because this is a convolutional neural network, a padding. And here we're going to say that if self.cube equal len equals 32 equals 32, we're going to say like pad, it will be equal to 111. So we need to create our layers, and to create our layers, now I hate that thing from Colab. Let's create our architecture. So we will say like self that layer 1 equals to self that conv layer, and here we're going to pass some arguments like self that C dimension. We're going to say like self that F theme do they do it like this? Oh, sorry, I'm trying not to. Yeah, F dimension. And we're going to multiply this first by 32. No, by 8. Sorry, by 8. We're going to apply kernel size. Remember that we saw in class the kernel size is basically like the amount of the size of the filters that we are applying. This will be 4. The stride will be 2. Remember, we saw the stride that basically was like the step that we're taking to go over the image. The padding pad. So basically, if we're using 32, we'll use the padding of 1. If not, we will just don't use any padding, and we will specify a bias, self that bias. All right. So here it's pretty straightforward. Actually, like if you remember our classes about convolutional neural networks, we saw that in general, it's like a pattern that repeats itself. So the only thing that we need to accommodate now, let's say, are our parameters. So for example, here for the second layer, our padding will be 111. And actually, we're going to use this here and this here. And we started with a dimension of 8. Here we're going to multiply this by 8. We're going to multiply this by 4, this by 2, and the self f dimension. This will be 4, 2 here times nothing. The kernel size will be constant for all the layers. The stride will be also constant, and the padding, it will be the same situation here. And the bias will be okay. So again, these are like all operations. We're applying all these convolutions now in 3D, but it doesn't change much from what we had in our DC GAN or things that we saw, and I gave you a call up about that to use with images, the one that I just showed. One major difference I will say is here that we will use, for example, a torch dot, and then we will create now our we're using torch sequential. We'll do a couple of interesting things, like for example, use now torch dot nn, and we will use a convolutional transpose 3D. So basically, it's the inverse of a convolution. So basically, this is like upscaling. So now when you apply the convolutions, we saw that basically it's applying filters and downscaling your image. But now we will do the opposite process. So in this case, is convolutional transpose 3D self that the F dimension. Here, same kernel size. We are using 4. Right to padding 111. What else do we get here? We need our activation function. In this case, we're using torch nn. That's sigmoid. And I think that with that, we have our next layer. Let me check if everything is okay. Yeah, it looks okay. Here we'll use def. We'll create a definition, conv layer, and here we're gonna do self input dimension, output dimension, kernel size. By default, we're gonna leave it at 4. We're gonna put the same arguments here. So let me just copy this. We're gonna add bias equals false. Is this okay? This is okay. And here we're going to say that layer equals to torch at nn, again, sequential. We're going to say here like torch at nn conv transpose 3D. Let me just copy this and we will modify so we don't have to write it all over again. The only thing that we're going to change is this is like the our parameters will be the input dimension, output dimension. The kernel size will be equal to kernel size. I want to hard code that. The stride equals to the stride. The padding equal to the padding. And what else we're missing here? Let me check. That looks good. And here we're going to add a torch.nn.sigmoid for our activation function. No, sorry. Here we're going to add the batch normalization, not the activation function. Batch norm 3D. The argument that we're passing is the output dimension. And here we're going to use torch.nn.relu. Why relu? If you remember from class, relu gets rid of all the negative values, right? We don't want negative values for our convolutions. You have seen for the special versions that you use leaky relu. Sometimes you want to have like a little bit of like a controlled negative values, but in this case, we're just using relu as the default operation. And now what we are going to do, we're going to define our forward definition. We'll pass like self and x, and we are going to say that out is equal to x.view -1 self that c dimension and 1, 1, 1. We will say that out is equal to self that layer 1 out. Oh, I'm putting a lot of typos today. I didn't have coffee today, so probably that's the reason. Self that layer 2 out self out will be basically we'll repeat this for all of our layers. So just let me I'm just gonna copy and paste. This is layer 3, 4. We need layer 5, and we need out equals to torch. This is our out torch. Sorry, it's torch that squeeze and out. Basically, what we are doing here. So if we analyze like what is happening here, that now that we establish all of our layers, for each one of this, we're gonna get a specific output. So for example, here the output will be 32 times 200, 32 times 200 times 111. From layer 2, we will get, sorry, from here, we're gonna get this. From 2, we're gonna get here an expanded version of that output. And in this case, this will be 2, 2, 2, if I'm correct. Here we will get a 32 by 128 times 444. Here we will get 32, 64, 888. So basically these are, you see that we are downscaling every time. 32, 32, 16, 16, 16. And from layer 5, the output, if we print, we are going to get in the end a 32, 1, 32, 32, 32. Yes, this is correct. Basically, this is the transformation of our network. Basically, you start with a batch. Basically, it's a latent vector of 200 units, one channel in each dimension, and then you start basically like formatting or reshaping that vector into something that has a structure that is a 3D structure, as you can see here, right? 32, 32, and 32. So this is our generator. Now we're going to do the discriminator. And the discriminator is somehow similar. We're going to do this, and then we are going to define. Actually, that will take a lot of time. So I will just copy and explain a little bit like what's going on, because again, I want to keep this as short as possible, because then we're going to save this locally and we're going to use it from another Colab to do the training. I mean, we can use this here, but we want to keep also like the Colab like short and not too messy. So we're going to do the generator, sorry, the discriminator. And the discriminator is, just one second. That's D, and the discriminator, again, we will take the torch dot NN, that module. And what we can do here is, again, we're going to define same thing here. This up. Super net G self it. And here we're going to say that our arguments will be like self at args equal args, self that q lan equal to params that q that lan q underscore lan, sorry. Or what did I do? There you go again. Leak value. We're going to define a leak value. Params leak value in a bias equals to params that bias. Again, a padding. It will be 0, 0, 0. We're going to use the same thing. So actually, I'm going to copy this. I'm going to put it here. If the length is equal to 32, we will just use the padding 111. self that f dimensions is equal to 32, and we will create our convolutional layers. So in this case, what we are going to do, we're going to do something that is pretty similar. So actually, I'm just gonna copy the first thing here. And this is pretty similar to what we now basically we want to expand the the output from our output from the generator, input that to our discriminator, and expand it and format it as a basically a 3D thing. So basically like a 3-dimensional matrix with values, in this case 0 and 1. So we will use something pretty similar. We will start here formatting our first layer. Our parameters will be, we'll start with the F dimension, the kernel size is 4, the stride is 2, just like the other one. The padding will say immediately that is 1, 1, 1. And the bias, self that bias. This will be our first layer. The rest of the layers will be identical. So actually, I'm going to be lazy and copy this. So this will be layer 2. The only difference is now we won't use this parameter here. The F dimensions we're going to multiply by 2. The kernel size will be 4, stride 2, padding 1, 1, 1, self that bias. And we will do the same thing here with the layer 3. Because again, we need to reshape the data in order to understand it as a 3-dimensional matrix. We are going to multiply the layer 2. No, with layer 2, we don't want to multiply by 2 the F dimension. We want to do it in the third layer. And I'm missing one parameter. Sorry. Actually, we want to do that. I want to do this here times 2. And then we want to repeat this argument here. The kernel size is 4. Comma. Kernel size is 4. You have this over there, 2, 2, 2, 1, 1, 2, 4. Yes, this is okay. Cell dimension is 4, and padding is exactly the same. And finally, now we can copy this. The layer 4 will be here will be 4. Here we'll expand this to 8. 4, 2, and the padding, blah, blah, blah. Those are our layers, and we will do a just like we did with the generator, a layer 5, and this layer 5 will be torch that, and then that's sequential, and do torch that, and then now we will do a convolution. A conv3d self that F dimensions. Here we will multiply it times 8. Then we'll have 1. Kernel size will be equals to 4. We're using the same parameter. Stride equals to 2. Bias will be self bias, and the padding equals to pad. And here our activation will be sigmoid. And we define now our convolutional layer, just like we did before. Do I have the right indentation? Yes, def conv layer self input dim output dim kernel size equals 4 stride equals 2 adding 111 equals. It's a bit of a pain, like writing all the parameters, and the bias equals to false, just like we did before. Now, with all of this, we will create a layer. We'll select torch, .nn, .sequential. And we're going to do torch.nn .conv3d. Input dimension, comma output dimension, comma kernel size equals to kernel size, stride equals to stride, comma bias padding equals to padding. We'll use batch normalization 3D, so torch and then batch norm 3D. Output dimension as the parameter. And here we'll do torch.nn that here, for example, we want to use leaky ReLU. I don't know exactly why we're using leaky ReLU instead of just ReLU. Why would you want to have like maybe negative values? That's a mystery. I will probably that's a question that we'll have in class. So I will see, because I don't remember. And I'm looking at that at my notes, and we're using anyway. Place here. Actually, I missed something here. In this here, we need to return layer. We want to do the same down here. We want to have the right indentation, so that's the right indentation. And now we create the network with our forward function. Self and x, and we are going to say that out x that view, this will be -1, self that f dim 1 out equals to self that layer 1 out, and we're going to do the same thing. 2, layer 3, layer 4, layer 5, out equals to self that, no, here now, this will be equals to torch that squeeze out, and here return out. So what we're doing here is let's write here the outputs, how everything will be transformed. So this no, actually this is not correct. This should be -1 sorry, self that cube len, self that cube len, self that cube len, comma, self that cube len. This is the right format for our first for the input of the discriminator. Why? Because if you remember, here we have this information here that is coming in this format. So actually we want to format this according to that, right? Otherwise it will give us an error. I was just repeating the first out of the generator. So this then will be shaped as a 32, 1, 32, 32, 32. This is what, sorry, this goes here. And this part, the output will be, and this will be converted into 32, 32, 16, 16, 16. Then this should be going to, I forgot to write this in my notes before. This should be like 32. Oh, but this is easy because it's just doubling. Like this number is gonna double, and this ones will decrease. This will be 8, 8, 8. For the next one, we'll have here a 32, 128, 444. Here, this will be 32, 256, 222. And finally, from layer, that's from layer 4, from layer 5, we will have a 32, 1, 1, 1, and 1. If I'm correct, because then, yeah, that is the format that we want. So this is our discriminator. So now we have these two layers, this layer, and we want to write the training function. Again, I'm not gonna write it from scratch because I want to keep it like just like this. This, we will define a trainer. And basically this will be, actually let me do it from, I don't know why I did that. The trainer. So let's just define our definition for a trainer. We want to save our output. So what we want to do here is something like this: establish a path where to save our epochs and stuff, because this takes a lot of time for training. So it takes hours. You want to basically like save every other time. If we want to use, for example, TensorBoard to then see again, you will see a lot of this like pretty similar code everywhere, because it's like one code that has been going through like several modifications. There are like good repositories. There was one very nice tutorial by Runja Tan at Digital Futures. Pretty similar code. The one that I show you is updated for Python 3, but it uses that MATLAB format, so you need to do stuff to work on that. I have another ones. Actually, this is the one that I've been using like for a while. And we want to now define our data set. Define the data set. And what we can do, we can say, for example, specify here with a specific name. So actually, let me see if I can use a couple of things that we did last time. Actually, I do have. So I have here the files from the last tutorial. But I don't know what is the resolution. Let me see if I can open one. Just with Notepad, at least the heading. Yeah, so these are 128 by 128. So it'll cause an error. I must have these are OBJ. No inbox. Okay, let me mount my Google Drive. Because I know that in my Google Drive I have some inbox files. Basically, you want to put that in here, that path that we're going to use. So let's say we're going to put our models here, like new folder. It will be like a data set. And under data set, you will have a folder with, I don't know, like chairs 32. Everybody's doing chairs, and someone asked me the other day, like, why everybody's using chairs? Because, well, architects love chairs, and yeah, getting the data set when this came out, it's like difficult, like to get like a lot of 3D models, because this was done by computer scientists, not good at 3D modeling, to do the tools for 3D modeling. So in order to get like meaningful stuff, they relied on the ShapeNet dataset. And one of the most complete categories on the ShapeNet dataset are chairs. So we can use like whatever you want. I mean, I showed you in the second video how you can create your own dataset. So whatever, let's just call it your own dataset. Custom 32. Let's say you're doing it with 32 by 32. So we want to just format everything. Actually, we want to do this. Because here we have the information about what we're going to train. Print datasets path. So we're creating a data set, and if we look at the actually, let me go to here. The original repo where we are basically like we're getting the code to this Colab, and the utils in order to create a data set, it has one specific function that is called class shaped net data set. And what this is doing here is actually converting those voxel formats into NumPy arrays. But it's using the get voxels from math definitions. So basically this is using this definition that is loading math files. So we're not going to use that. So we're going to use a modified version. So don't despair, because in the next session, actually, we're gonna learn how to modify that. Actually, and we're gonna, as I said in the last lesson, we're going to implement that inside a specific source file. Sorry, a utils file where we will have the same or similar functions but adapted for this. So for now, don't despair. We're gonna say like something like, in this case, train these sets equal to convert to Winbox. This will be our convert to Winbox, and we're gonna give the datasets path, sorry, our arguments, and we're gonna say that this will be our train dataset. So again, we will implement this function here. The utils file, utilities file. We can do a couple of things here. Train dataset loaders. And here is like a lot of like parameters and things that I will just copy. We will define our models. The generator and the discriminator. We need to use a criterion for, so let's do a couple of things here. We are going to add a solver for the discriminator that will use an Adam optimizer according to the parameters that we will establish, like a learning rate and the beta value. Also, we'll add a solver for our generator with those parameters that we will fine tune. The parameters to device to actually use this and the GPU. If you're trying to run this on your CPU, you're doomed. It's not gonna happen. Also establish a criterion for the discriminator and the generator. So basically, these are the losses that we're using. Mean square error loss for the discriminator, and L1 loss for the generator. And what we are going to do is just define, I will just copy paste because the code is like super long, super long. I'm going to share it. But the important is like, I wanted you to see the architecture of the network. So basically this is just like a very long training loop that is going through like each epoch, setting a time and basically running. So you can say that here, for example, it's like generating the latent vector and then it's training the discriminator, and then it trains the generator. So basically it generates another latent vector. This will generate something that will go through to the discriminator again. It will say like this is fake or real, and you will adjust everything, and then you can basically like save images of your information. So if this is correct, I mean, this should again, these are just the basic functions that we're going to have. So in the next session, we're going to implement this code. We're going to have some basically we're going to have a version. We're going to keep adapting this. Basically, we're going to clone this repo, and we're going to use it to actually train our network. But I wanted, based on what you have seen in class, this idea of two networks, in this case, one that is like doing some convolutions to generate something from noise, and the other one that is just interpreting this to the right format, is something that I wanted to show in this video. So let's wait for next lesson. I'm going to put like here, this is part 3, GANs. And hopefully in a couple of days, I will upload the next video. So thank you very much, and see you.